Today's word is curiosity. What are you curious about? Could it be thermodynamic system and the first law of thermodynamics? Do those terms sound new or exciting to your ears? Well then, allow us to spark that curiosity. I'm Rafa Jane Lagumbay Ubanan and together with my groupmates, Aiko Balanay, Gabriel Lopez, and Salud, we're here to guide you through the fascinating world of thermodynamics. By the end of our discussion, you should be able to first define a thermodynamic system, identify its types, properties, processes, and applications. Second, to explain the first law of thermodynamics, its formula with sign convention, and apply it to problem solving. And third, to evaluate the first law's limitations and assumptions and demonstrate its applications through examples. What is a thermodynamic system? Thermodynamic system is a system of matter and energy confined to a defined region of space that may exchange matter and energy with its surroundings. This means that the system under study is isolated in a specific area and it has the ability to interact what's outside it, either by transferring energy like heat or work or matter like gas or liquid. The behavior of this system, including how it changes over time, depends on these interactions. Another is thermodynamics works by exchanging heat and mass with the environment surrounding the system. The system is not entirely sealed off from the outside world. It can absorb heat, release energy, or lose or gain mass through various processes. These exchanges drive changes in temperature, pressure, volume, and other properties within the system. Everything outside the system is called the surroundings. And the surface that separates the system from its surrounding is known as the boundary. The boundary can be fixed or movable, and it determines how energy or matter can be exchanged. The surroundings refers to everything external to the system. The boundary acts as the dividing line between the system and its surroundings. This boundary is important because it dictates whether and how energy or matter can flow in or out in the system. For example, a fixed boundary might not allow volume change, while a movable boundary, like a piston, allows the system to expand or compress. Overall, a thermodynamic system is a defined space where matter and energy interact with their surroundings, and understanding its boundaries and exchanges is key to analyzing physical and chemical processes. Now that we understand what a thermodynamic is, let's explore its three main types. The three main types of thermodynamics, starting off with the open system. An open system is a system that can exchange both energy and mass with its surroundings. So as you can see, the energy transfer is present in open system as well as the mass transfer. An example of this is a boiling pot of water without a lid. No, heat enters from the stove, which is the energy, and steam escapes into the air, which is the mass. So both energy and matter moved in and out of the system. The second is the closed system. So a closed system can exchange energy like heat or work, but not mass with its surroundings. As you can see, energy transfer is present, but the mass transfer is not present or applicable in closed system. An example of this is a sealed metal container being heated, or heat can enter or leave. Not it is called energy, but the gas or liquid inside cannot escape. That's why mass is constant. And the third is the isolated system. So an isolated system does not exchange energy, no, either energy or mass with its surroundings. So that's why energy transfer and mass transfer is not present in isolated isolated system. An example of this is a perfect thermos battle, which is ideal case. No heat enters or leaves, and no matter is added or removed. In reality, no system is perfectly isolated, but this is a useful idealization in physics. Therefore, understanding the three types of thermodynamic system, which is the open, closed, and isolated, allows us to analyze how energy and mass interact with the surroundings, providing a fundamental basis for studying physical and chemical processes.
Let's talk about the two properties of thermodynamics. So first is the extensive properties. So these depend on the amount or the mass of substance present in the system. Let's take for example mass, which is the total quantity of matter in the system. Now for the volume, so this specifies as the space occupied by the system. Next we have internal energy. So the total energy, so kinetic plus potential, which is stored in the molecules. And of course the enthalpy, the total heat content. The entropy, which is the measure of disorder in the system. So let's take note that if you double the amount of substance, these values also double. So that means they are additive. Now, next property, we have intensive properties. So they do not depend. So as we talk about the extensive, they depend, right? So here in the intensive properties, they do not. So they do not depend on the mass of the system. So let's take for example the pressure. Of course, the pressure force is force per unit area, and when we say temperature, this measure the average kinetic energy. For the specific volume, this is volume per unit mass, and for the specific internal energy is that internal energy per unit mass. So for the specific enthalpy or the H and the specific entropy or the S, same concept, so per unit mass. So let's take note that these remain the same even if the system is divided or the size changes, so they are non-additive. So next we have the four basic types of thermodynamic process based on which property is kept constant during a process. So the first one is what we called the isobaric process or the constant pressure. So this pressure remains constant while other properties like volume or temperature may change. So let's take for example if we are boiling a water in an open pan. So pressure stays atmospheric, right? So this is an expansion or compression of gas in a cylinder with a movable piston or constant pressure. So next we have the isochoric process or the constant volume. So this talks about the volume remains constant, meaning no work is done by the gas. Let's take for example heating a gas in a sealed rigid container. So any heat added changes only on the temperature and internal energy. So those are the number 2 process. Now let's move on to the number 3, which is the adiabatic process. So there is no heat transfer here. No heat enters or even leaves the system. So let's take for example a rapid compression or expansion in an insulated cylinder. So any change in energy comes from work done on or by the system, but not from heat. So last process we have the isothermal process or the constant temperature. So this temperature remain constant since we are talking about constant temperature. This is all about isothermal process. So let's take for example the slow compression or expansion of gas where heat exchange with surroundings is possible. So the key point here is that internal energy doesn't change at all, or all energy exchange is as work or heat. So again, those are the 4 process of thermodynamics. So again, we have the isobaric process. Second, we have isochoric process. Third, we have adiabatic process. And last, we have the isothermal process. And again, there are two properties, the extensive, which is the additive, and of course, the internal property, which is the non-additive. So those are the two properties and the four processes of thermodynamic system.
Today I will be discussing about different applications of thermodynamics. So thermodynamics is the study of heat, energy, and work. So first is engineering. So thermodynamics is essential in designing car engines, airplanes, power plants, and refrigerators. So an example for this is the internal combustion engines in cars. So they use thermodynamics principles to convert fuel into motion. So second is the chemistry. So in chemistry, it helps predict whether a chemical reaction will occur or how much energy is involved. So for instance, the exothermic reaction, like the reaction between acid and base, release heat, which can be measured using a thermodynamic. Next would be the biology. So in thermodynamics, it explains how organism uses energy. So a good example for this is the cellular respiration, where glucose is broken down to release energy, which is the ATP in our bodies. And of course, in our everyday life, so we experience many thermodynamics in our daily activities. So for example, for this is the boiling water, cooking food, and using air conditioners. So and charging our phones. So it involves energy transfer and also heat flow. And that will be all about the application of thermodynamics.
The first law of thermodynamics. It states that energy can be converted from one form to another with the interaction of heat, work, and internal energy, but it cannot be created nor destroyed under any circumstances. Energy can be created or destroyed, only transferred or transformed. The total energy of an isolated system remains constant even though energy may change forms. So let us now proceed on how to solve problems in a thermodynamic system given this formula. Change in internal energy is equal to Q, or heat added to the system, minus W, or work done by the system. Here are the sign conventions. Q, or heat, positive when heat is added to the system, and it is negative when heat is released by the system. Work, positive when work is done by the system. It is negative when work is done on the system. While internal energy, positive means internal energy increases, while negative means internal energy decreases. So here are some problems for us to solve and to learn how to calculate thermodynamics. Example number 1. A system absorbs 800 joules of heat and thus 250 joules of work. Let's find the change in internal energy of the system. So here are the given. Q, or heat, that is equal to positive 800 joules. Why positive? Because it is added to the system. And W, which is work, that is equal to positive 250 joules. Why positive again? Because it is done by the system. Using the formula change in internal energy, that is equal to heat added to the system minus work done by the system, let's find out the solution. Let us just substitute what are the given. Change in internal energy is equal to 800 joules minus 250 joules, that is equal to 550 joules. So therefore, the change in internal energy is 550 joules. Example number 2. A gas releases 400 joules of heat and 150 joules of work is done on it. What is the change in internal energy? Given Q, which is heat, that is negative 400 joules. Why negative? Because the heat is already released by the system. W, which is the work done, that is negative 150 joules. Why negative? Because again, the work is done on the system. Using the formula again, change in internal energy that is equal to heat released by the system minus work done on the system. Let's find out the solution. So change in internal energy is equal to negative 400 joules minus negative 150 joules. Minus to minus, that is equal to negative 400 plus 150 joules equals negative 250 joules. So therefore, the change in internal energy in this problem is negative 250 joules. So since we are done solving the change of internal energy with both positive and negative, now let's see what we can solve if we will find the heat or Q. Here is the example. A system does 150 joules of work and its internal energy increases by 350 joules. How much heat was added? Given W or work done, that is equal to positive 150 joules. Why positive? Because work is done by the system. Change in internal energy, that is positive 350 joules. Why positive? Because internal energy increases. Given the formula, Q is equal to internal energy plus W or work done, let's find out the solution. The solution is heat is equal to 350 joules plus 150 joules, that is equal to 500 joules. So therefore, 500 joules of heat was added to the system. Let us also figure out on how to find work or W. In this example, a system absorbs 600 joules of heat and its internal energy increases by 400 joules. Let's calculate the work done by the system. Given Q or heat, that is positive 600 joules, the internal energy is positive 400 joules. Given the formula, W or work is equal to heat minus internal energy, let's find out the solution. Simply distribute the given. W is equal to 600 joules minus 400 joules, that is equal to 200 joules. So therefore, the work done by the system is 200 joules. So that's it. I hope you learned a lot on how to solve thermodynamics using those formulas.
The limitations. First in the limitation is the direction of heat flow. So the first law doesn't explain why the heat naturally flows from the hot to cold. Only the energy is conserved during the process. So the first law of thermodynamics ensures that the conservation but that does not dictate why the heat naturally transfer from the hotter body to the colder one, which is explained in the second law of thermodynamics. So the second one is the feasibility of process. It doesn't predict whether the process is spontaneous or not. For example, it doesn't explain why the heat can be extracted from ice by cooling it, requiring external work. So, while the first law accounts for energy balance, it does not determine whether the process occurs spontaneously, such as the need for external work to extract heat from the ice by cooling it further. So the third one is the complete work conversion. So it doesn't state that the heat can be completely converted into work, which is a practical limitation. So the first law states that the heat and work are interchangeable, but does not assert the heat can be fully converted into work without losses, which is practical constraint addressed by the thermodynamics efficiency. So the fourth one is the equilibrium assumption. So the first law primarily deals with the system in equilibrium or transitioning between equilibrium state. So this law primarily applies to the system in equilibrium or transitioning between equilibrium states, limiting its ability to describe rapid and non-equilibrium phenomena. So next is in the assumption. So the first is in the assumption is the isolated system. So the first law is often applied to the isolated system where no energy matter enters or leaves. So these are systems with where neither energy nor matter can be exchanged with the surroundings, ensuring the total internal conservation. The second one is the equilibrium state. So it assumes the system are in the thermodynamics equilibrium, meaning that the properties like temperature and pressure are uniform throughout. So the system is in the thermodynamic equilibrium when all properties like temperature and pressure remain uniformly described without spontaneous changes. The third one is the reversible state. So the first law is often used to conjunction with the concept of reversible process, where the system and surroundings can be returned to their initial state. So this process is allowed the system and its surrounding to the return of their initial state without any loss or dissipation of energy. So the last one, the fourth one, is the quasi-static processes. It often assumes the process occurs slowly and gradually, say, allowing the system to remain. This occur infinitesimally small steps, keeping the system in equilibrium at every stage to approximate idealized thermodynamic uh, behavior. So let's proceed to the application example. So the first one example is the refrigeration cycle and how the refrigerator operates. So vapor compression or refrigeration cycle, where the refrigerant absorbs heat from the inside of the fridge and releases it outside. So I will going to explain how each part function in the process. So first is the evaporator. So the evaporator is located inside the fridge. It absorbs heat from the food and the air inside, causing the refrigerant to evaporate into a low pressure vapor. Second one is the expansion valve. So the refrigerant process passes through the expansion valve, where it expands and it pressure that drops significantly, which causes it to become a cool fluid ready to absorb heat again. So the third one is the radiator fence. So these fans help dissipate heat efficiently, improving cooling performance by increasing heat surface area for heat transfer. So the fourth one is the condenser. So the condenser is located at the back of the fridge. Here are the high pressure vapor releases its heat to the surroundings, returning into the warm fluid. So the fifth one is the compressor pump. So the compressor pump acts as the transforming it into the high pressure vapor and increasing its temperature. This ensures the efficient heat release when the refrigerant reaches the condenser. So the second example is the calorimeter. Calorimetry. So calorimetry is the science of measuring the heat transfer from the system. Is often used to determine specific heat, enthalpy changes, or thermal energy in reactions. So here are some functions of each components. So first one is the stirrer. As you can see here, the stirrer used to ensure the uniform mixing of the solution, preventing the temperature gradients with the isolated cup. So this ensures the accurate heat distribution. So the second one is the thermometer. So the thermometer measures the temperature change in the mixture before and after reaction to calculate heat absorbed or released. So the third one is the cover. So the cover prevents the heat to lose the surroundings, improving the accuracy of calorimetric measure by minimizing the external influences. So the fourth one is the insulated cup. So often a calorimeter designed to minimize the heat exchange with the environment, ensuring the precise temperature changes in the mixture. So the fifth one is the solution mixture. So the substance undergoing the heat exchange, where either an endothermic absorbing heat or exothermic releasing heat reactions.
Application and example number three. So, metabolism. It is a process by which food is converted into energy. So, food is converted into energy, which is then used by the body to do different activities. So, the body loses energy through heat, work, and stored fat. Food intake is to replace lost energy. So, four is chemical reaction. So, and endothermic, the surrounding heat absorbed through the ice cube, which resulted melting. So, and exothermic naman, flames release heat to the surrounding area, causes warm effect. So, an example number five is car. car uses engine that burns fuel to create energy. So this process follows the first law of thermodynamics, which states that energy is always conserved. It can't be created or destroyed, only changed. In short, the engine converts fuel's energy into motion, but some energy is always lost as heat.
We're now to the conclusion about thermodynamic system and the first law of thermodynamics. Understanding a thermodynamic system allows us to focus on the part of the universe where energy changes occur, whether in engineering machines, chemical reactions, or living organisms. The first law of thermodynamics, which states that energy cannot be created or destroyed, only transformed or transferred, served as a foundation for analyzing these changes. It emphasizes that any heat added to a system is either used to do work or increase the system's internal energy. While the law ensures energy conservation, it does not predict the direction of processes or energy quality, which are addressed by other thermodynamic principles. Nonetheless, it is a powerful tool for designing efficient systems and understanding energy flow in the real world. Therefore, the thermodynamic system and the first law of thermodynamics highlight how energy is conserved and transferred between a system and its surroundings. This law explains that energy cannot be created or destroyed, only transformed or used to do work. This understanding is crucial for solving real world problems in physics and in everyday life. Our reference for this presentation is from Britannica, where we gathered reliable and well explained information. We truly appreciate your time and attention. Thank you for listening. We hope you learned something new and valuable today. Bye and have a great day ahead.